the limit superior of a sequence of reals always exceeds any term of the sequence. Do we know? Maybe I should just strike that from the record. I'm sorry. I thought no. The limit superior of a sequence. You know what that is from analysis? You have A1, A2, A3. This is your sequence, AJ, 111. Okay? And what you do is you say A sub n is defined to be the set starting at n and going up. Okay? And then you take the supremum the supremum of the elements of A sub n. That would be the largest of these, plus a little skosh more, right? I mean, it is either one of these or it's a limit point of this sequence, right? If this thing goes off to infinity, it's no longer bounded, and you'd have to say the upper limit or limit superior is infinite. But then if this is bounded, what happens is this. There's a supremum for this. It may have been the case that the supremum needed to be where it is because there was a term prior here that was large. But as you clip the terms off, as n goes up, you're clipping stuff off the front end. So what happens to the supremum? Let's call this A alpha. Alpha sub n is the supremum of this set. And this set is from n up. It clips the first n minus 1 terms. So here's what happens. Alpha 1 is here, alpha 2. The alphas come down, right? And if the alphas approach a limit, that's the limit superior. Because after a while, you pass a finite number of things that require the supremum to be up here. And then you reach it's sometimes called the greatest limit. Then there's a least limit. If the sequence has a greatest limit and a least limit that are the same, it has a limit. It always has a greatest and it always has a least. They may not be the same. Here's an example. Here's a sequence. Minus 1 over n. Oh, sorry. Minus 1. Minus a half. 3 halves. Minus a quarter. 1 3/4, 7 fourths. So this sequence is jockeying around here. The negative numbers are coming up, the positive ones are going up too. So the lim inf, so-called inferior limit, least limit, after I clip a finite number of these terms, in this case it would be 0. You know, minus 1, minus a half, minus a quarter, minus an eighth, minus a 16th, and everything. Right? You're coming up. The least limit is 0. The greatest the greatest limit though is going up 2. Yeah, add a quarter, add a half, add a quarter, add an eighth. So the superior equals 2. They both exist and they're not the same. So this sequence certainly doesn't converge. But if you clip arbitrarily many terms at the front end of it, where you are is never much more greater than 0, and never much more greater than 2, and never much less than 0. That's the idea of the greatest and least limit. It's a thing that happens, even if the sequence doesn't converge. You get beyond it, and you get below it. And then you start throwing out stuff at the front end. And all that can happen is these things ratchet together, because it may be the reason this had together is because an early term was big, or another early term was small. You get past them, throw them out, the soup and int get closer and closer. It'd be nice if they converge to the same value, in which case the sequence would converge. But you'll take what you can get. So you might converge to a limit superior and a limit inferior. And they're just different, which means the sequence spends its time shuttling around there. Right? You get the concept? Okay.
We can scratch that question.
I can scratch that one.
What was it true?
No.
That's fine.
Yeah. That's what can happen is, here's an example, counterexample. It'll be this sequence. Minus 1, 1. Minus 1/2, 1.
I knew you were going to do that.
Okay. So the limit superior is 1. None of these terms are greater than 1. And the lower limit is 0. The limit inferior is 0. So this doesn't converge. The upper limit and the lower limit, there's space between them. There's a lump there. There's a lump, no convergence. But it does have, you would write down the lim soup is 1, the lim int is 0. Sometimes the lim soup is written like this, and the lim int is written like this, and there's all kinds of little formulas with these things in them. Sort of little identities. You know, if you have two sequences, you like to know stuff like this, right? And all kinds of little identities like that. It's worth investigating once in your life. But don't fret. We're doing mostly negotiation stuff. Order completeness and uniform completeness is the same for the reals. Matt asked me that ages ago. Yes, that's true. And every open cover of a set of reals has a Levade. It has to be a special set of reals. It has to be compact in order to have a Levade. So that. That's that. So I'll be. I know this is difficult stuff. I'll just change it here. I won't make it terrible.